I want you to take a second and look at the closest physical object to you right now.
Yeah, maybe it's the phone in your hand or like a cup of coffee on your desk.
Right, or even just the fabric of your shirt. Now think about the food you ate for breakfast, or the medicine in your cabinet, or, the very skin on the back of your hand.
Which is kind of crazy when you think about it.
It is. What if I told you that almost every single one of those wildly different things shares the exact same fundamental elemental DNA? Welcome to our deep dive. Today, we are tearing into a comprehensive science chapter dedicated entirely to one specific element, which is carbon.
And our mission today is to really figure out the ultimate chemical paradox.
Exactly. We are looking at a single element that makes up a shockingly tiny fraction of our planet, yet acts as the ultimate molecular Lego brick, basically building the entire biological and modern world.
The raw numbers behind that paradox are genuinely difficult to wrap your head around when you first read them in the source text.
Oh, they're staggering.
Right. Because if you sample the Earth's crust, carbon only accounts for about 0.02%.
Wait, 0.02? That's nothing.
It's microscopic. And mostly that's locked away in minerals like carbonates or in coal and petroleum. And if you look up at the atmosphere, it's just 0.03% in the form of carbon dioxide.
So we're talking about a profoundly microscopic inventory of raw material here.
Exactly. Yet, despite being so scarce, carbon is the undisputed, non-negotiable foundation of all living structures. So the question we really have to answer is how a material with such a limited supply manages to dictate the architecture of practically everything.
Okay, let's unpack this atomic personality. Because to understand how carbon builds the world on a microscopic budget, we have to look at how it interacts with other atoms.
Like the bonding.
Yeah, because a lot of chemistry is about stealing or giving away electrons to reach a stable state. But, carbon doesn't do that. I like to think of carbon as a roommate who refuses to buy their own TV, refuses to let you sell yours, but absolutely insists that you pull the couch into the middle of the room so you can both watch it at the exact same time.
That is actually a perfect analogy. That concept of mandatory sharing is the absolute core of covalent bonding.
So why is it forced to be the annoying roommate?
Well, to understand the mechanism behind why carbon is forced to share, you have to look at its atomic structure. Carbon has an atomic number of 6.
Okay, 6 protons.
Exactly. 6 positively charged protons sitting in its nucleus and 6 negatively charged electrons orbiting around it. 4 of those electrons are in its outermost shell.
The valence electrons.
Right. Now, the driving force of chemistry is that every atom wants to reach a stable, noble gas configuration, which generally requires having 8 electrons in that outer shell.
So carbon is sitting at 4, and it needs to find 4 more to reach that magic number of 8.
That is the dilemma right there. Let's look at the physics of its options. Carbon could try to steal 4 electrons from other atoms to form an anion.
But it can't, right?
No, because it only has 6 protons in its nucleus. The electromagnetic pull of 6 positive protons is simply not strong enough to hold on to 10 wildly moving negative electrons. The atom would become incredibly unstable.
Okay, so stealing is out. What about giving them away?
It could try to just shed its 4 outer electrons to form a consolidation, but stripping away 4 electrons against the pull of the nucleus requires a massive input of energy.
You'd just be ripping it apart.
Yeah, you'd be left with a tiny nucleus desperately trying to hold on to just 2 electrons. It's energetically impossible under normal conditions.
It's completely backed into a corner. It doesn't have the gravitational pull to steal, and it doesn't have the energy budget to give away.
So it compromises,
Wow.
shares. It offers its 4 valence electrons to other atoms, provided those atoms offer their electrons in return.
And they just sit in the middle.
Pretty much. Those shared pairs of electrons sit right in the space between the 2 atoms. The positive protons in both nuclei are magnetically attracted to that shared negative electron cloud in the middle.
Like a mutual tug of war.
Exactly. And that shared attraction acts as a literal electromagnetic glue, allowing everyone involved to feel like they have a full, stable outer shell.
Wait, if these atoms are just engaged in a mutual tug of war over this shared electron cloud, that sounds like a tenuous arrangement. If nobody actually owns the electrons holding it together, why don't carbon compounds just fall apart at room temperature?
That's a great question.
Yeah.
We have to distinguish between the bond inside the molecule and the attraction between different molecules.
Okay, break that down for me.
The covalent bond within the molecule is incredibly strong. Carbon is a physically small atom, which means its positively charged nucleus is very close to those shared outer electrons. It grips that shared electron cloud tightly.
But what about between two different molecules?
That's where it gets weak. The force is holding one individual molecule to a completely different molecule. The intermolecular forces are very weak because the molecules themselves are neutral. They haven't formed charged ions.
Oh, I see. So the bricks themselves are indestructible, but the mortar holding the bricks to each other is flimsy.
That is the perfect way to put it.
Yeah.
And that explains the physical data we see in the text. Methane, which is just one carbon atom sharing electrons with four hydrogen atoms, has a boiling point of only 111 Kelvin.
Which is what, like negative of 160-something Celsius?
Yeah, roughly negative 162 degrees Celsius.
Yeah.
Chloroform, ethanol, acetic acid, they all have incredibly low melting and boiling points because it takes very little heat energy to separate the molecules from one another.
And I'm guessing that lack of ions affects other things too.
It does. Because these molecules are electrically neutral and don't form free-floating ions, covalent compounds are generally terrible conductors of electricity.
So if carbon is this desperate to share electrons, what happens when there's nothing around but other carbon atoms?
Oh, it turns out, carbon just starts building with itself, and this is where its versatility literally explodes.
Because carbon doesn't just form one uniform crystal, right? It shapeshifts based on the geometry of how those atoms lock together.
Yes.
And here's where it gets really interesting. The source text highlights maybe the most absurd reality in all of chemistry. The hardest substance known to humanity and the smooth, slippery stuff inside your pencil that conducts electricity are the exact same pure element.
You're referring to the allotropes of carbon, so diamond and graphite.
Right.
This shapeshifting happens because of two properties. First is tetravalency, meaning carbon has 4 electrons available to form 4 bonds. Second is catenation.
Catenation.
Yeah, which is carbon's highly unusual ability to form incredibly stable long chains, branches, and rings entirely out of itself. When you apply those traits, the geometry of how they connect dictates the physical reality of the substance.
I am looking at a pencil right now, and reconciling that the lead inside it is chemically identical to a diamond ring is baffling. How does merely changing the angle of a bond create two completely opposite physical materials?
Well, what's fascinating here is that in a diamond, every single carbon atom uses its 4 valence electrons to form strong covalent bonds with 4 other carbon atoms.
Making it rigid.
Right. It creates a perfectly rigid, interlocking, three-dimensional network. There are no loose ends, no free electrons. That dense, unyielding 3D grid is what makes diamond the hardest natural substance we know of.
Okay, but graphite doesn't do that.
No, graphite takes a completely different architectural approach. Each carbon atom only bonds to 3 other carbon atoms, and they form flat, two-dimensional layers of hexagons, kind of like a sheet of chicken wire.
But wait, carbon still needs to satisfy that rule of 4. If it's only bonded to 3 neighbors in graphite, there is a valence electron unaccounted for.
Good catch. That 4th electron ends up forming a double bond within the hexagonal ring to satisfy the valency.
Oh, okay.
And because graphite is arranged in these distinct flat layers, stacked on top of one another with very weak forces between them, those layers can literally slide past each other.
Like cards in a deck.
Exactly.
Yeah.
That sliding action is what makes graphite smooth and slippery enough to use as a dry lubricant or as the core of a pencil.
And what about the electricity part?
Crucially, the nature of that specific bonding structure leaves free electrons that can easily move through the material, which makes graphite an excellent conductor of electricity, totally defying the normal rule for nonmetals.
The text also notes something fascinating about diamonds, actually. You don't have to wait millions of years for the Earth to crush carbon into a diamond.
Right, synthetic diamonds.
Yeah. We can make synthetic diamonds simply by taking pure carbon and subjecting it to immense pressure and temperature in a lab. They are indistinguishable from natural diamonds because you are just physically forcing those carbon atoms into that interlocking 3D grid.
The physical conditions simply force the geometry to change. And, the text introduces a third class of pure carbon allotropes that were discovered more recently, the fullerenes.
Oh, yeah, the soccer ball one.
Yes. The most famous is C60. It is a discrete molecule made of exactly 60 carbon atoms bonded together in pentagons and hexagons, forming a perfect hollow sphere.
And they named it Buckminster fullerene, right?
Yeah, after the American architect Buckminster Fuller, because its structure perfectly mirrors his geodesic domes.
A microscopic carbon soccer ball. But as interesting as pure carbon crystals are, the natural world isn't just diamonds and pencil lead. The real complexity happens when carbon starts letting other elements into its molecular network.
And this brings us to hydrocarbons and heteroatoms.
Right, the customizer aspect of carbon.
Exactly. Carbon forms this incredibly stable scaffolding, just chains of carbon atoms bonded to each other, surrounded by hydrogen atoms.
Like butane.
Yes, butane is a great example. It's 4 carbons and 10 hydrogens. Those 4 carbons can be arranged in a straight line, or they can branch off into a T-shape. The chemical formula is identical, but the physical shape is different.
And the text calls those structural isomers.
Correct.
I picture that carbon-hydrogen skeleton like the blank metal chassis of a car. It's the foundation, but it doesn't really do anything interesting on its own.
It really doesn't.
The text mentions that you can pluck off just one of those hydrogen atoms on the chain and replace it with a different element, like oxygen or halogen. But does swapping out one single atom at the end of a massive chain really rewrite the identity of the entire molecule? Like, does the tiny tail wag the giant dog?
Oh, the tail absolutely dictates the behavior of the molecule.
Yeah.
It all comes down to chemical reactivity.
Because the chassis is just stable.
Exactly. Those carbon-hydrogen bonds making up the chassis are incredibly stable and unreactive. They're just along for the ride. But when you introduce a heteroatom like an oxygen, nitrogen, or chlorine atom, you're introducing an atom with a different electronegativity.
It pulls on electrons differently.
Right, it is highly reactive. Chemists call these functional groups. Whether it's an alcohol group, an aldehyde, a ketone, or a carboxylic acid, that specific functional group becomes the site where all future chemical reactions take place.
So the carbon chain is essentially just a handle, and the functional group is the blade of the knife.
That is a brilliant way to put it. That concept perfectly frames what the text calls a homologous series.
Which is when the functional group stays the same, but the handle gets longer.
Yes, exactly.
Yeah.
We can look at a family of compounds where the functional group stays exactly the same, but you just keep adding links to the carbon chain handle. Let's trace the alcohol family as our example.
Okay, let's do it.
You start with methanol, which is 1 carbon atom attached to an OH alcohol group. Add 1 carbon and 2 hydrogens, so a CH2 unit, and you get ethanol with 2 carbons.
And then add another one, you get propanol.
Exactly. As you climb this ladder, adding CH2 units, the molecule physically gets heavier. Because the molecular mass increases, the physical properties show a highly predictable gradation.
So things like melting and boiling points change.
Yes, they steadily rise. But because they all share that exact same OH functional group, their chemical reactivity remains virtually identical.
So what does this all mean in practice? Let's look at what happens when those specific functional groups interact with the real world, starting with human biology.
Biological systems are very sensitive to these structures.
Right, because we just established that methanol and ethanol are essentially chemical siblings. One just has a slightly longer carbon handle. If their chemistry is so identical, why is ethanol safely processed by the body in beverages and medicines? But methanol, just one rung down the ladder, is intensely lethal.
It's a brutal demonstration of how biological systems interact with functional groups. While the OH group reacts similarly in a test tube, the physical size of the molecule determines how our enzymes process it.
So our body treats them differently.
Very differently. When someone ingests methanol, it travels to the liver where enzymes immediately oxidize it, stripping away hydrogen to turn it into a compound called methanol.
Methanol with an A? I mean, it sounds so similar to methanol, but the biological impact is devastating.
Because methanol is highly reactive with organic tissue. It aggressively interacts with the components of your cells, causing the protoplasm to coagulate.
Oh, that's horrifying.
The text uses a very visceral comparison for it, actually. It says it's exactly like dropping a raw egg into a hot pan. The clear proteins instantly denature and turn into a solid white mass.
And methanol does that to your cells.
It does. It also specifically damages the optic nerve, causing rapid irreversible blindness, often followed by death.
Wow. Meanwhile, ethanol, with just one extra carbon atom, doesn't get converted into that specific cellular poison. It depresses the central nervous system, causing intoxication, but it certainly doesn't cook your protoplasm.
Right. Small changes, massive differences in biology.
And the text notes ethanol is equally fascinating outside the body, in the laboratory. Like, if you take ethanol and heat it up with concentrated sulfuric acid, you completely transform the molecule.
That reaction highlights sulfuric acid's role as a dehydrating agent.
Meaning it pulls water out.
Exactly. The acid physically forces the ethanol molecule to give up an OH group from one carbon and a hydrogen atom from the neighboring carbon. Those combine to form a molecule of water, which just leaves the system.
So what happens to the carbons left behind?
The two carbon atoms, now suddenly missing their partners, have no choice but to form a double bond with each other to satisfy their valency. The ethanol alcohol has been converted into ethene, an unsaturated hydrocarbon gas.
So you literally wring the water out of the molecule to change its structure. Another reaction the text highlights is esterification.
Oh, this is a fun one.
Yeah, you take ethanol, and this time you mix it with ethanoic acid. Ethanoic acid is commonly known as acetic acid, right? Like, it's the active ingredient that gives vinegar its sharp, sour taste and smell.
It is. And the source text mentions a great physical detail about ethanoic acid, actually. Pure ethanoic acid is called glacial acetic acid because its melting point is 290 Kelvin.
Which is pretty warm for a melting point.
Yeah, it's about 17 degrees Celsius, meaning it can literally freeze into solid crystals on a cool winter day.
Hence the word glacial.
Exactly. So when you react this sharp-smelling acid with an alcohol like ethanol, they undergo a condensation reaction. Again, a molecule of water is shed, and the two compounds fuse together to form an entirely new class of compound called an ester.
You would assume mixing a strong alcohol and a sour vinegar acid would create something harsh. But esters are practically the opposite of that.
They really are. Esters are highly volatile, meaning they evaporate into the air very easily, and they are characterized by their sweet, pleasant smells.
Like artificial flavors.
Yes. The vast majority of artificial flavorings in foods and the synthetic fragrances used in perfumes rely entirely on the specific structure of different esters.
So carbon functional groups dictate the perfume we wear and the alcohol we consume. But I guess the most common way humans interact with carbon is by destroying it for energy. Combustion.
Right, burning it. Carbon compounds, especially hydrocarbons, store an immense amount of energy in their covalent bonds.
So you introduce oxygen and a spark, and boom.
You break those bonds, releasing heat and light. But the efficiency of that reaction depends entirely on the structure of the carbon molecule and the availability of oxygen.
Give me an example of the ideal scenario.
Well, if you burn a saturated hydrocarbon, where every carbon is attached by a single bond and fully loaded with hydrogen and provide plenty of ambient oxygen, the reaction completes itself perfectly. You get carbon dioxide, water, and a clean blue flame.
That's what you want to see when you turn on a gas stove. But anyone who has cooked over a campfire or a faulty burner knows that sometimes the bottom of your pots get coated in this thick black soot.
And that soot is a real-time visual indicator of incomplete combustion.
Because something's going wrong in the reaction.
Right. If you're burning an unsaturated hydrocarbon, meaning there are double or triple bonds, or if your oxygen supply is restricted, the chemical reaction simply cannot finish the job.
So it just leaves carbon behind.
Yes. The fuel breaks down, but there isn't enough oxygen to convert all the carbon into carbon dioxide gas. The unburned carbon particles are swept up in the heat, creating a yellow, luminous flame, and they deposit on your cookware as black soot.
It's literally wasted fuel sticking to your pots.
Precisely. If your gas stove is leaving soot, it means the air holes in the burner are obstructed, starving the reaction of oxygen.
Which brings up fossil fuels, doesn't it?
It does. This mechanism of combustion directly connects to our use of fossil fuels. Coal and petroleum were formed from ancient biomass, trees, ferns, and microscopic sea life that were crushed under geological pressure over millions of years.
But they aren't pure hydrocarbons.
No, because these fuels originated from living organisms. They contain trapped nitrogen and sulfur. When we combust them today, those heteroatoms react with oxygen to form oxides of nitrogen and sulfur, which are major environmental pollutants.
It's fascinating that the same element responsible for the soot on our cooking pots and the grease from our foods is also the fundamental building block of the exact thing we use to wash it all away.
Oh, soap.
Yes. I want to talk about soap because how a bar of soap actually works at a molecular level feels like magic. We know oil and water famously repel each other, so how does soap force grease and water to get along?
If we connect this to the bigger picture, soap is a marvel of applied chemistry. The text defines soap as the sodium or potassium salt of a long-chain carboxylic acid.
Okay, what does that look like?
To visualize it, imagine a molecule shaped like a tadpole. The head of the molecule is ionic. It carries an electrical charge. Because water is also a polar molecule, this charged head is hydrophilic.
Meaning it's intensely attracted to water.
Exactly. But the tail of the molecule is a long, uncharged hydrocarbon chain. This tail is hydrophobic. It is repelled by water, but it readily dissolves in oils and grease.
So you have a molecule with a split personality. When I have greasy dirt on my hands and I introduce soap and water, what is the actual mechanical process happening on my skin?
The soap molecules act as microscopic mediators by forming structures called micelles.
Micelle.
Yeah. The moment the soapy water hits the greasy dirt, those hydrophobic tails frantically try to escape the water. So they stab directly into the droplet of oil.
And the heads.
Meanwhile, all of the charged hydrophilic heads stay facing outward, actively interacting with the surrounding water. They basically arrange themselves into a microscopic sphere around the oil droplet.
The dirt gets completely encapsulated, like a microscopic search and rescue team.
Yes, it is trapped in the center of the micelle, and because all of those outward-facing heads carry the same ionic charge, they electrically repel each other.
Which keeps them separated in the water.
Right. This repulsion prevents the individual micelles from clumping back together into a big greasy mess. Instead, these little spheres stay perfectly suspended in the water as a colloid.
Is that why soapy water looks kind of murky?
It is. This colloidal suspension is actually why soapy water looks cloudy to the eye. The suspended micelles are physically large enough to scatter passing light. When you turn on the tap, the water washes away the hydrophilic heads, taking the trapped dirt right down the drain with them.
It is a brilliant system, but the text outlines one major chemical flaw that humans had to engineer their way out of. Soap completely fails if you are using hard water.
Oh yeah, hard water is the enemy of traditional soap.
Why is that?
Well, hard water contains naturally dissolved calcium and magnesium salts. When traditional soap molecules encounter these specific ions, a replacement reaction occurs.
So they swap places.
Pretty much. The calcium and magnesium ions essentially kick the sodium off the soap molecule and attach themselves to the long carboxylic chains. This new compound is no longer soluble in water.
Oh, no.
Yeah, it immediately falls out of the solution as a white, curdy precipitate.
I'd call that soap scum.
Exactly. It is highly inefficient. The hard water actively consumes your soap to make scum before any micelles can form.
Which is why it's so hard to build a lather in hard water, and it leaves that stubborn residue on your clothes and skin.
Yep, and this is exactly why detergents were invented.
Ah, okay. So how do detergents fix the scum problem?
Detergents follow the exact same hydrophilic head and hydrophobic tail blueprint, but they use a different functional group for the head. Instead of a carboxylic acid salt, detergents are usually sodium salts of sulfonic acids or ammonium salts.
So they just swap the head.
Right. The crucial difference is that these specific charged ends do not form an insoluble precipitate when they react with calcium and magnesium. The micelle structure survives intact, allowing detergents to remain fully effective even in the hardest water.
You know, when you zoom out and look at this entire journey, it borders on the unbelievable. We started with an element that accounts for just 0.002% of the Earth's crust.
Which is basically a rounding error.
Exactly. But because of its unique physical dilemma, its forced necessity to share 4 electrons, and its architectural ability to chain together with itself, it generates nearly infinite variety.
Yeah, it's the ultimate molecular Lego.
It really is. Just by altering its geometry or swapping out a single functional group, carbon gives us the rigid diamonds in our jewelry, the sliding graphite in our pencils, and the dense energy of fossil fuels. It gives us sweet-smelling esters for perfumes, lethal compounds that coagulate cells, and the micelle-forming soaps we use to wash our hands.
It is the ultimate testament to the foundational rule of chemistry, which is that molecular structure determines physical function. The simple physics of how one small atom balances its protons and electrons dictates the complexity of the entire biological world.
Which brings me to one final thought, something for you to mull over after this deep dive ends. The source text briefly brings up the element silicon.
Right, carbon's neighbor.
Yeah, if you look at the periodic table, silicon sits directly below carbon. It also has 4 valence electrons. It also tries to share them, and it also attempts to chain together with itself.
But it doesn't work out as well.
No, the text notes a critical failure. When silicon forms chains with hydrogen, those compounds become highly reactive and completely unstable after reaching just 7 or 8 atoms.
The physical constraint there is size. Because the silicon atom is significantly larger than carbon, its positively charged nucleus is physically farther away from those shared outer electrons.
So the magnetic pull is weaker.
Exactly. The electromagnetic grip is weaker, making the bonds inherently fragile.
So carbon's ultimate superpower isn't just that it shares electrons, it's that it is perfectly geometrically small. Its bonds are tight enough to be stable, but flexible enough to build endless complexity.
It's right in the Goldilocks zone.
It is. So, as humanity peers through telescopes, scanning distant exoplanets and searching the universe for extraterrestrial life, we have to ask a profound question. Is carbon the absolute only atom in the universe with the perfect geometric balance, small enough, stable enough, and versatile enough to support the insane chemical complexity required for life to exist?
Or is our imagination just strictly limited by the chemistry of our own planet?
Exactly. The next time you pick up a piece of plastic, or drink from a cup, or just look at your own hand, remember, you are looking at the universe's ultimate, irreplaceable masterpiece of sharing.